Hello folks, hope everybody's doing well, and today I'd like to start with a little bit of homework that I gave out yesterday. I'm not sure anyone did it, but I did the homework. That's important. I did the homework. The homework was, for those who who still remember it, the homework was trying to figure out how these threads go through a ring. In other words, how they go down a torus. I had put this, where is it? Let me put this black thing in there to cover this up first. Is it torus? Here it is. We had the torus. And as you can see, the torus is kind of curving inwards. So we're going to make the assumption that there's a magnetic field going down that hole and out through the outside. In other words, that's rolling around it. Essentially, what we're looking at is the following. We have, let's see if I can find it here. We have atoms, which I put in there a few atoms to show the motion of the atoms. The atoms are spinning. In this case, they're spinning inwards. So they're going to be sweeping the threads into the hole downwards and upwards on the outside of the torus, of the ring, or the donut, whatever you want to call that. So the issue is the following. The atoms are spinning, and we got to figure out how we're going to be pushing threads through that little hole and out the outside. And there are a few conceptual problems that need to be resolved. Turns out that yesterday, we had a 2-hour powwow with my son after we adjourned, and we dealt with some of these issues, and today I try to illustrate them for you. Okay? Anyways, this is the first illustration that I'm going to show you here, and it's the field. And I did my best here. I'm not the best artist in the world. Like I tell my son, I hope to be the worst and remembered as the worst. I want to be up there with Dali and Picasso.
What the heck is that?
Well, you got to look at it a little while.
I want to.
That's the field, the magnetic field, and it's pushing down the center downwards and coming out the outside. So if you look at it carefully, what you've got in the first torus, you don't have the atoms visible. In the second one, you have the atoms twirling. And in the third one there, you have the atoms twirling. They're pushing the field into the hole and out the outside. And that's about the best I could do. Okay, so you got to look at it very careful to see what I try to draw there. Okay, now it's a little choppy because there's only four different pictures there.
Can you slow it down, the GIF?
I could. I probably had one around there that is slower than that. In fact, I sped it up. It was even faster than that. But the bottom line is there's only four pictures, and that's why it's a little choppy. Of course, if we put 10, 20, 30 pictures, it's going to look better, and maybe if I slow it down, I don't know if that would help. But the bottom line is what we're seeing here is on the green side, the green on the inside is surrounded by the yellow, surrounded by the blue. Okay, I try to separate those three colors. And the one on the inside, the green one, is pushing into the hole, and essentially it has no interference. The yellow one has a little bit of interference, and I'll go over that in a minute here, why there is some interference. And then the blue one is on side, all of them, because it just can't get into that little hole. So it's circling around in a very narrow spot when it tries to go through the hole. Okay. And what is happening here? Well, in order to see what's happening in a magnetic field, what the magnetic field does, we got to look at how iron filings scattered over a magnet, really over, in this case, I'm going to show two wires running current in the same direction. And let's see if I can find it. Here we have the iron filings pointing in a given direction. Both these wires, the little black holes in the center, they're coming into your eyes. Okay, the current is running into your eyes in both of them. They're running current in the same direction. And if you sprinkle iron filings over those two wires that are attracting each other, if you keep the wires separate so that they don't attract, but you know that they do attract because the current is running in both wires in the same direction, that's the pattern you would get if you sprinkle iron filings over it. And if you compare that against the repulsion pattern that we get, which is that one there, you can see that we do have a difference. And in this case, the one on the right, you have one wire running current into your eyes and the other one running in current in the opposite direction. If you sprinkle iron filings over those two wires, you get that pattern. And you can see the two patterns are noticeably different. The attraction pattern shows some kind of circular pattern around both of them, whereas the repulsion patterns show like two circles each around each of the two wires. And one thing that I like to point out, at least in the right hand side, which I think is quite obvious, is that you can see like they're trying to squeeze something through in between them, and it's like, you know, that dark band that's trying to get in there. It can't get in there for some reason. It's if you look at it, it's just circling around both wires and trying to get in there, and it can't get in there because the density is too high. That's what that pattern shows to me, and we're going to see that that is exactly the case. And what we got to look at here is that these are magnetic fields, and as both Mr. Faraday and Mr. Maxwell said, you know, there is matter in motion in that region. So the mathematicians will tell you something about lines of force and tell you that they're abstract, that they're not real. Well, that's not what Mr. Maxwell and Mr. Faraday, who studied magnets probably a lot better than a lot of these people today do. And they had a different idea. They said, look, there is matter in motion. We just don't know what it is, but there's something in motion in there. So what the iron filings do, they just line up along that thing that is moving in there. Okay? And so how do we explain this under the rope model? Let's see if I can find it here. Here's the iron filings for the attraction. And what we have is, again, we have two wires. You can see them on the right. And the two wires are made of countless atoms. I've drawn, about 8 on each side. And they're spinning the threads in the same direction. In other words, in this case, they're spinning them clockwise. Okay? So current is running into your eyes. And because they're spinning the threads in the same direction, when the threads on the one on the left come up and they latch on to the threads coming down on the one on the right, that's what pulls the two wires together. That's the physical mechanism of attraction. If you look on the left-hand side, you will see what the patterns are really showing, the iron filing patterns. You see that, well, this is the second part here, and now we go into the third part. Let's go into the first part. The first part shows, I think it's in green, shows that two circles. Yeah, there you go. So what the threads are doing there is just circling each wire. That's it. There's no interference. They're just spinning threads at great speeds around each of the wires, and they're not being bothered by the threads of the other wire. It's when you get to the second part, the, what is it, yellow? Gotta wait, yeah. The yellow one there, you can see that there's an interference. One swings it around, and then the other one kind of interferes with it and pushes it away. It doesn't let it complete the entire circle. And then the last one, the blue one, just goes around both wires because it just can't get into that region between the two wires. Okay, so those are the patterns that I see forming in there. And with the threads, we can explain that very easily. You can see on the right-hand side, when they're farther apart, they can circle easily around each of the wires. When the wires are close, in this case, what we're trying to imitate is what happens when the threads interfere. well, then they form that figure 8. And then when they're, when they can't get in there at all, then they circle both wires. That's essentially the analogy there.
Why did you move the 2 wires together in the right one?
Yeah, it's just a simulation of why the threads can't get in between the 2 wires. That's the only thing I'm trying to show there. It's a little misleading because that's not what's happening on the right, on the left. The left picture doesn't show that there's any movement of the cables, okay? And all I'm saying is that in the on the right-hand side, when the 2 wires are apart and the threads can get through without interference, they just form the circle. When they get closer, and again, it's not that the wires are coming closer, I'm just saying when there's interference in the threads, that's the pattern you will see. And when there's total interference, when the threads can't get in between the 2 wires, then you get the blue one there. You get, the threads are just going around both wires. Okay, that's the only thing I'm trying to show there. And we see the opposite with the iron filings in the case of repulsion. I think it's this one here. Here you can see a different pattern. And I like to use the analogy that this is like 2 rollers of an old washing machine. You try to push your shirt through there and it squeezes the water out. And that's the way I see this. It's like, those rollers that you had and you put something between the 2 rollers and it just squeezes it out. And imagine if you threw sand between 2 rollers, right? And the 2 rollers are going in the opposite direction. Well, the sand is just going to accumulate and go right through that narrow spot. And that's, I think, what we're seeing here.
In the earlier one, I always called the earlier one like
this one here,
the same direction one.
Okay, this one.
Conveyor belt.
Okay,
shape.
Yeah, that's a good analogy.
But it's
also
very telling that they're both circular motion things. We're talking about like the magnetic fields are always circular. So that's very telling in what's going on. You don't have corners in.
It's like fields. Something's orbiting.
Yeah, it's like skipping a rope.
Well, how do you create circles? You create them by rolling a thread around, a rope around, whatever. Then you create a circle. Yeah, you're talking about circular motion, then you're saying that they're orbiting a center of mass or whatever. Even if you look at mass,
these are round no matter how you spin it.
Yeah.
The first one, when they're in the same direction, is like a conveyor belt. In fact, that's what they use some things for. They move it around.
Yeah.
They move things forward. While
and
the other
one
is just like you said, it's like the washing machine.
Yeah, here you're squeezing water out of a shirt.
Through the 2 because they're both going in opposite directions. I mean, you could perfectly imagine this with rolling pins or the way the roller works. If they're both going in the same direction, they have a assembly line, conveyor belt kind of feel to it. While if they're both going in opposite directions, that's exactly what you'd expect.
Yeah, and so so one of the things that I'm trying to show here is that the iron filings, I think, are lining up with the motion of the threads around there. The question now comes, how are these threads put in there? How are these threads? Do they interfere with each other? Because one of the things that you will find in the literature out there, let me put our picture back in there. Where am I? Here, over here. One of the pictures that you will find, or one of the comments you will find out there is that the thread, or not the threads, the lines of force, the magnetic lines of force never intersect. They never cross each other. And we had a discussion last night with my son about that. Is that possible under the thread theory? Is it possible for the threads not to align?
What do you mean exactly by the lines of force do not interact?
Well, I had
intersect. Sorry,
I had a couple pictures here, but I'm not sure I raised them. I think we can see it maybe in the torus field here. Let's see if I can put that one up there again. I'm not sure that's very helpful either. But just imagine all those threads going through the center. okay, if you have all those threads, you would think that at some point some of them have to, like, they're bunching up. And you can say, well, they're pushing each other aside because there's so many of them going in there. But none of them intersect. None of them just cross each other, like, they go through each other or something. That's the point that I'm trying to make here. And the standard, the official version is that they don't intersect. And we had a long talk about that yesterday. Is that possible with the threads? And my bright son, he came up and he says, maybe they're staggered. In other words, maybe they are coming in different planes. And here I try to draw that as best I could. Let's see if I can find it. Here it is. Remember that when you give that first atom in the long line of aligned atoms or aligned molecules that form a wire, you plug it into the wall and suddenly there's electricity running through there. And in this case, we have the electric current running opposite of your eyes. It's going clockwise and it's swinging the threads in the opposite direction, as you can see the threads being built, because there's a reason for that. In other words, the first thread is there, right? Then comes the second, the third one, and the fourth one, but they come at a different angle. In other words, they don't come one on top of the other.
Like a rainbow?
Yeah, in other words, what they're describing, they're all at different angles. That's the issue. Therefore, they do not interfere. They do not cross each other.
But that is to say that they're not over each other like a rainbow.
Right. They're not like a rainbow, or like we said yesterday, the McDonald's sign. In other words, the threads do not overlap in the sense that if you cross these threads, like if you take one right next to the other, they would necessarily cross each other. But if you take them at different angles, then they don't cross each other, and that's what I'm trying to show there. I'm trying to show that if the wire is swinging clockwise, right, the first thread that comes out, the first one that is triggered, is going to be the one between the first two atoms. And then the next one could be, for example, between 1 and 3, and then 1 and 4, 1 and 5, and so on down the line. That's what we're showing. One with 2, 1 with 3, 1 with 4, and so on down the line. And these threads are coming at different angles, and that's why they do not interfere with each other.
Essentially what you're saying is, it isn't that the magnetic lines or they're all on top of each other so that it's like a wall that's going around. You're saying that these arcs, each arc takes up a different spot in the 360 degrees allotted to them.
It's a different angle. And if you try to do the same drawing, if you try to draw this, which is what I tried to do in the past, I don't know if I have a picture of that. If you try to do the same drawing, all on the same plane, they will intersect. There's no way you can avoid it, especially when you connect 2 with 3 and 3 with 4 and 4 with 5, and then you go with 2 with 6 and 2 with 7. They're gonna cross each other. If you put them all on the same plane, okay. And what we're saying here is that they're not on the same plane. The other thing this shows is that when the atoms, the row of atoms is twirling, right? It's spinning, the serpentine. The first atom is the first one that's going to turn. So it's got to have an advantage over the first and third, the first and fourth, the first and fifth, and so on down the line. It's going to have an advantage in the timing. That's the first one that gets swung around. So what we're seeing here also is why there's a little bit of torsion along the wire. The magnetic field is a torsion that's moving down the length of the wire when you turn the electricity on. In other words, the row of atoms are spinning, but the first one spins before the second one, and so on down the line. And so they should be staggered also because of that. And this also explains, again, why there's this helical motion of so-called electrons down the wire there is no helical motion of individual electrons. What you have is a serpentine of interconnected atoms or molecules. Again, I never try to clarify which one because I really don't know which one. But one of the two has to be the one that carries the so-called current down the road. What it is a serpentine that, what I called it, I say that it's a worm on which you throw acid and it's twirling in place. it's kind of coiling in place.
What was that hexical motion you were talking about?
Hexical motion.
You just said it's not
helical
motion. Yeah, what's helical?
Well, it's like the screwdriver, not the screwdriver, the drill bit.
Okay.
You know, the drill bit has this coil in it,
Yeah.
right? So if you look at a drill bit, you know it's coiled, right? And that's what it is. When you turn it around, what you'll see is that coil. And that's what I'm saying is that all these atoms that are connected one to each other, the whole entire row is like I call it a serpentine, you know, but it's like a drill bit. You can use any analogy there. And if you turn one around, the first one will turn before the second one, before the third one. So that's got to create some kind of helical motion, not only in the atoms, but also in the magnetic field that's going around it. And the magnetic field is built out of the threads in this case.
Does that mean that you could have a magnetic field that pushes something along the wire because it has that drill bit motion?
Say that again?
If the magnetic field is spinning like a drill bit along the wire, couldn't it?
Well, no, the magnetic field is around the wire, not along the wire.
Yeah, but along the wire as well, because if it's staggered like that, then it gives this
okay, but hold it.
serpentine shape.
Yeah, but hold it. Let's make sure we understand the difference there.
Yeah.
In electricity, and that's one thing I keep saying because people forget this. They want to introduce the rope or the thread. Electricity is a row of atoms. In other words, it's atoms that are spinning. Whereas the magnetic field are the threads that are going around them. Okay, so, and that means that if we're going to talk about like electricity, you know, we're just talking about all these atoms in a row and they're all connected and they're spinning. Whereas the magnetic field is just the threads swinging around them.
Yeah, but you're talking about this serpentine shape. Since the first one starts and it's small, then the second one, then the third one, then the fourth one, it gives this
coiling.
The magnetic field essentially coils. It doesn't coil, that's the wrong word. But if you aggregate all the lines, all the jump ropes, the magnetism, you get this serpentine essentially drill bit looking shape.
Yeah, you do.
So, but just like a drill bit pulls up dirt from these machines that they drill into the ground and they pull up dirt. The drill bit's staying in place, but the dirt's moving up. Could you similarly, maybe with a very small iron filing or something, push it along the wire?
Well, you can't push it along the wire because the wire is made out of atoms. So I don't know. I mean, there would have to be to the side, next to it. That's
I guess it would just get stuck to the wires.
Yeah,
that's all you get.
I'm not sure if you could do that. I mean, electricity. I'm not sure you could drill or you know, play bowling next to this thing. What you're saying? Can I roll a ball down that? I'm not sure you can do that. You know. Anyways, I wanted to show that, and unfortunately, I'm not a good artist, and I take a lot of pride in that. Okay, let's see. I have so now. Well, once we have the field, and here again, let me put the field up there one more time, and I'll start with the color black because I only have three pictures there, and one's going to be the torus. And the other one's going to be the torus atoms that are twirling around. We can all more or less see those two very clearly. The one's not very clear is the third one here, which is, where is it? This one here. Here's the field, okay? And the field is really supposed to show that, you know, the magnetic threads, the threads are pushing into that hole when the atoms are twirling, atoms are spinning there on the upper right, and so they swing the threads into the hole, and I was able to draw it. It's a monster to draw this with only 4 pictures that you got there, and which makes it look so choppy. But I could visualize what how they could be pushing threads through there. If we take this torus now and we put it onto a galaxy, we get something like this. Here's the galaxy, and now we're going to put the field in the center, right? Because the magnetic field is running through the center of the galaxy. And here I took the black out. See if you can still see that. Okay. And so supposedly the threads are going into, again, from north to south in this case. They're going from up to bottom. They're going through the center of the galaxy. I removed the black here so that you can see the threads more or less there. And that's what's happening inside the center of the galaxy. No black hole, no mystery there with no mystical things. And I did it with a second galaxy. I don't know if it's seen in a better light here. Where is it? Let's see if I can find it. Here it is. Here's the other galaxy. Maybe this one you can see it better. Again, I put the threads in there, the field. They're turning the threads around, they're twirling them, and the threads go through the center of the galaxy downwards and out through the sides of the galaxy. So the magnetic field of a galaxy does extend beyond the edges of the galaxy. I think it does help to maintain the integrity of a galaxy. But there you get an idea of what it might look like in real life. I'm sure some better artist than me can do a better job. Maybe we get Dan or Dave. Dave did a good job with the Pressy on the atom, so maybe he can work on this as well if he's interested. But essentially what I'm trying to show is that the threads are going through the center of the galaxy there. Okay.
How is the galaxy magnetic?
Galaxy becomes magnetic because all the suns, all the stars that form the galaxy contribute thread to it.
What do you mean by contribute thread?
And this has something to do really with, let me put ourselves here back again. Last night, like I said, I had a little discussion with my son. Not a little one. We lasted 2 hours talking about the subject. He came, 2 hours. Yeah, we were till nighttime. Anyways, there's something that's interesting that came up. One of them was a staggering. He came up with that idea. He came up also with another idea, which I thought was very interesting, made me change my mind. And let's see if I've got a picture of that.
Hold on, I still wanted to ask about the galaxy.
Yeah, I'll get to the galaxy. Okay. Hold on. Yeah, because it's
Same
got to do
topic
it.
on me.
No. It's got to do with that. It's not. I'm not trying to put you
away
off.
from the question here.
I want to see if I can find. I do have that somewhere, but I've got so many of them here. Let's see if I can find it. Oh, yeah, here. Well, here's one of them. This is good enough. Here you can see 2 atoms, and they're connected by a rope. They start twirling, and one of the ropes comes loose. Well, my son says, what if both threads, one of the threads comes loose? That's what I meant to say. What if both threads comes loose? One goes to one side, the other one goes to the other side. And that's one possibility. Another one is the entire rope starts swinging. Those are 3 possibilities. In other words, the way I envision this is one thread comes out loose. Another possibility is both threads go in opposite directions and form arcs. So it's not lopsided like it is now, it's symmetric. And the other one is that the rope swings around. And I kind of liked his idea better. I think it's better than this one. I think the 2 threads are probably swinging in opposite directions. Okay?
180 from each other?
Yeah, I would say that they form 2 arcs, one on each side. So maybe the magnetic field is comprised of 2 arcs on both sides simultaneously.
They form an oval.
Yeah, it forms some kind of oval or circle or whatever you can imagine that as. And now we can get back to your question. All the stars, they have a magnetic field.
Well, what was the question?
Oh, the question is, Oh, now I got to tell you what the question is. Okay, I see.
How is the galaxy magnetic?
Yeah, okay. And so now that we clarified that, I wanted to make sure that we got that point in there. So there's three possibilities there. One is the one that I came up with originally. One thread remains straight, the other one swings around. I don't think that's the best possibility. I think the better possibility is the one he mentioned yesterday. That's the two threads going outwards and they're swinging in up, essentially like I always like to use the analogy of the paddle wheels of a riverboat. The one paddle comes right after another, but there's a paddle on the other side as well. So one comes down, the other one comes up, and I think that's what they're doing. Okay, and that's probably the better option. And then the galactic field. What happens there is that all the stars that comprise a galaxy, they contribute thread, they contribute ropes. They're swinging. You got to remember these stars and so on. They have a lot of matter in them. There's a lot going on in each star. Just look at our sun. They've analyzed it back and forth, and there's a lot going on in the sun. A lot of simple to some degree, but at the same time, it's wondrous. It shows you that these flares come out, and when the flares come out, you see these arcs, and you're saying, what's that arc? And I'm saying it's the magnetic field going through there. But if there's a magnetic field, meaning the threads, they're going through that region, they're circling. Something created them, and those are electron shells that are merged together. They're forming serpentines. They're twirling the threads around. We see the effect of the threads going through the fire, and you see all this fire coming down, whatever it is, gases, whatever's coming down there. But you see the threads going. Oh, well, you don't see the threads, but you see the magnetic field kind of forming those arcs. But if that's, and I think they all agree that that's created by the magnetic fields, if that's the case, which I agree, by the way, then it's got to be, where does it come from? Well, it comes from serpentines, which are twirling inside the sun. They're swinging these threads around. And if the sun has the ability to have that electricity where all these atoms are twirling around, maybe in a torus fashion like I showed a minute ago, well, some of those arcs go very far away, and some of those threads. And you can see it in the sun itself. The magnetic field of the sun extends way beyond Pluto. I mean, it's humongous. And the sun is just a tiny little pebble in the scheme of a galaxy. And this magnetic field is really extending very far away.
Are you essentially saying that the suns in a galaxy take up the spot of the atoms that you showed in the torus? So essentially, the suns are all the atoms.
Yeah.
That are essentially doing the job of the that you showed in the torus just now.
It's possible that that's one solution. You can say,
because all the atoms in one sun are connected to the other sun too.
Well, there's another way of looking at this. One is that all the suns are spinning. That's one possibility. Another possibility is that within each of those suns, within each of those stars that are at least close to the center of the Milky Way, for example, I think that within each of those suns that form like a torus around the center, there's got to be, electrical serpentines. In other words, maybe in toroidal fashion also within each one of those stars. And they're swinging threads around. These threads are coming out and coming through the center of the galaxy and going out.
Wait,
and I think you have that all the way.
But then there's two different scenarios.
Yeah.
Because one is what I said, where the suns where the suns act like the atoms in the torus, where the connection between the suns are causing this torus-shaped magnetic field, which is this galaxy. But you're saying that every sun is an individual unit of it is its own torus, and when you aggregate a whole bunch of toruses along the torus of the galaxy, then you get this galactic magnetic field.
Yeah, in other words, there's two things we have to keep in mind, and from where the galactic magnetic field comes from. Each sun is, I think, has to be formed in a toroidal manner. In other words, if I were working from the center of a star outwards, I think I would find, circles. And all these circles are just alignments of atoms
More like
because of gravity. They're aligned in such a way that they form toruses or circles. And there's probably atoms, and chains of atoms, and there's probably chains of molecules, because maybe at least momentarily some molecule might form here and there in some reaction. But I think that whole thing is what we would see if we go from the inside of the sun outwards. We would see rings. A star is made out of rings. And those rings are created by the gravity, the pressure of matter coming into the center. Why does it want to go to the center? Because it's being pulled from every atom towards the center. And if you look at that, if you take an atom that's outside of the sun, right at the surface, if we could say, okay, here we have one at the surface of the sun, what is it being pulled by? It's being pulled by every other atom because it's connected to all the other atoms. So it's going to try to go in that direction. And where's that direction? The center of the sun. And the atom on the other side of the sun has the same problem. He's coming inwards. And the guy from the side is coming inwards. So that's why that pressure is what's creating the gravitational attraction towards the center. And it's
Where does the magnetism come in?
And the magnetism comes in because all these atoms now are aligned in a toroidal fashion around the sun, from the center outwards. And they're spinning, and again, I got to show the torus. Yeah, they're like the donut, and they're all spinning inwards and out from the outside. And, they have no room because then you got another toroid behind you, another toroid, there are all these levels of these shells of toroids.
Real quick, but that means down the center, the y-axis of from the vertical center, the vertical center of the sun, there's a lot of lines of magnetic force, or threads
squeezing through there and coming out. And that's why I think that's so powerful, because this thing is going very fast. The threads going through the center of this, let's call it the shaft.
Yeah, the well.
There's the shaft that goes through the center of the sun. Let's assume a perfect field, which it's not, but let's just assume
it's
it
close,
for. Yeah, it's again, all these atoms have to be aligned in some way, and they go through this shaft. Think of it as dropping, threads. What could you be dropping there? Well, you got to think of something trying to slide through there. Okay, all these threads are sliding through the shaft, coming out the bottom, coming on the outside, and coming back in. So it's forming this. And why? Because the ones that are close to the center, they're trying to swing their threads and they can't because the other guy's there. And so they're causing all this pressure of threads that finally come out the sides of the star, the sun in this case. And, that's the magnetic field that the threads are going to come through the shaft again, right down the center and back up, if we're talking about north-south, right? And I think that's the way that star is doing, a star like our sun is doing it.
Okay.
Now, but all these suns, remember that the magnetic field of the sun extends very far out. And you're saying, how can that possibly be? Well, because the pressure in there is so great of threads that these guys, they have to expand. They have to look for a space. All the threads can't fit inside the sun, so that they have to go around the whole solar, cocoon.
I thought it had to do with the distance between the atoms within the sun. So an atom, the magnetic rope that's swinging around between the two atoms on the edge of the sun, that magnetic line is extremely far out because the distance between the two atoms is very big. I mean, the sun's huge. I mean, you told me yesterday that this small atom already has is sending its magnetism far.
Yeah, here we have one of those magnets that we have here, and I was telling him that the magnetic field of this little thing is all the way out here. It doesn't just stop here. Most of the threads go in this region, and that's where most of its visible or detectable power is, or that's when it still has that magnetism that we can all see. But the magnetic field extends far out, and you're saying, well, what is it? Well, hold it. But what is that magnetic field? And I'm saying that's threads that can't fit in this region, and so they're all, far away from the magnet. We should be able to see, if we had God's eyes, we should be able to see a thread. The last thread is probably, I don't know how far away. I don't want to even guess that, but it's got to be quite far away.
Why is it so far?
Well, because it can't fit. I think that what happens, all these threads kind of, there's gazillions of threads here, and they kind of pile up, and it's like they can't get in there. And again, it may have to do with this issue of not not cutting across another thread. They're all lined up in such a way, staggered and so on, but they don't interfere with each other. They don't cut across other threads.
Are you saying?
And so they kind of pile up.
That to avoid piling up, essentially when the 360 in a certain distance is taken up, the line just takes the next distance over.
Yeah. It's like I can't interfere with the other guy underneath me.
Occupied.
The space is occupied.
360 1 centimeter away is occupied, so I'm going to do 1 meter plus 1.
Right, and so what happens is now the thread has to find its own spot, and the spot is far away as possible, and I think that's what's happening.
Okay,
the threads keep piling up. If you got gazillions of threads, where are you going to put them? Yeah. So they have to pile up.
It goes further and further out to just not interfere.
And this explains something also. This notion, and that's why is the magnetic field more powerful close to the sun, and less powerful farther away. Same with the Earth, and same with every magnet, whatever you take. The field is always strong near the center, or where the object is, and as you get further out, it gets weaker. You get the square of the distance phenomenon, and this explains it. I mean, if we're going to talk about real things, a thread is a real thing, and the more you get in close to the magnet, there's going to be more threads there bunched up. But as you get farther out, it gets less dense until you finally find the last thread of maybe this magnet.
So you're just getting hit by one thread.
Yeah, that's the last thread that has anything to do with that magnet. That's swinging around who knows where. And it's probably several meters away. And that's what's happening to the sun. The sun is this little, but its magnetic field is out billions of kilometers. And you say, well, how can that possibly be? Well, if we're going to talk about a physical item, it's going to have to be a thread. Otherwise, what are you going to say? A potential at each point in space? What does that mean? What's in there? Is there a dot there? Well, what is there? Why is it powerful near the sun and weaker farther away?
Back to the galaxy.
Yeah.
Are you saying that, so every sun essentially has a donut, a huge donut, going completely out of it. So the galactic magnetic field is a combination of all these donuts?
Again, you got to look at a couple things. One could be the torus, or the toroidal pattern formed by all these stars that are, for example, close to the center of the galaxy. Those have to be relatively close by. As you get further out, the stars get more normalized. Like, farther out, I would think that the stars have more distance between them than right at the center. The center, they're kind of bunched up. And as you go out, there's the stars have more distance first. And second, they're probably not affected by as much power, gravitational power and magnetic power as those that are close to the center. Now, does this mean that the stars close to the center of the galaxy are touching each other? No, I don't think so. I don't think there are stars that touch each other. And so you don't have electricity in the sense of, the electric universe, wants to propose, which is that, you have electricity across the galaxies. That's nonsense. And they do it with plasma because obviously they realize they can't do it with stars. It's not like stars are connected to stars. But electricity means
really powerful
electricity
wire.
means something is connected to the other one. That's why these people don't understand what electricity is. They cannot explain electricity. If electricity is atom against atom all bunched up in the sense that they're all connected,
there can be no electricity.
There can be no electricity in the galaxy in that sense. But then you say, well, where does the magnetic field come from? Well, that means that every star produces its own magnetic field and contributes to the magnetic field of the entire galaxy.
What do you mean by contributes?
Well, it contributes its threads.
Aggregate of donuts.
We're talking about an aggregate of threads.
But donuts, they're donut shapes.
Shape.
Every star is a discrete donut.
Well, it's not a donut. Remember, it's a collection of donuts. It's
No, it's a donut. A star has the donut torus magnetic shape. So when you talk about an aggregate
it's a weird
suns,
donut.
when you talk about an aggregate of suns, you're talking about an aggregate of donuts.
Yeah, but hold
bigger
it.
Donut.
Yeah, in a way, you're saying that if the magnetic field goes through the center, it's a donut that has no hole, almost, in that sense.
What?
It's a donut that has no hole. It's a round donut without a hole.
Yeah.
It doesn't really have a shaft. I use that as an analogy, but what's going through there is the threads. The threads can get in there, but they kind of squeeze themselves to go through that center or that y-axis, as you said, the y-axis of the star. The threads are trying to creep in there. They're trying to slide in there, and they can do so. Of a star. Of a star. I'm talking about a star. So the threads are going through there, and they're squeezing in there, like where have it here?
Donut.
No, not the. No, I want to show the pattern of the squeezing pattern, repulsion, attraction. No, repulsion. That's the one I want to see. See, I think you see.
Real quick, I like the fact that the torus shape or a donut shape is always repulsion. It always works on repulsion.
Yeah,
mechanics.
see here you see the picture. Mm-hmm. The picture is that I think that's what we would see inside the sun.
Real quick, that's a donut that
a
you
toroid
see from the side that you cut in half.
Correct. You cut in this case no, because you have the remember the wires coming one. The current in one goes in the opposite direction to the other.
But that would be the left and right edges of the donut.
Correct. This mimics quite well what's happening inside the star, because again, inside the star, it's like if I were to cut it in half, I would see.
One, what do you call that? One frame. Like
it's a cross section. If I take a cross section of the sun, I would see that in the one on the right. The black hole on that little dark. I hate to talk about black holes. The wire on the right, that's exactly what we would see in the sun. The electricity on that side of the sun is going in that direction, and the electricity on this one is coming in this direction. So that's exactly what we would see. They're going in opposite directions. They're spinning the threads in both in opposite directions against each other, and that's because you cut it in half as if it were a toroid that's cut in half. You cut the donut in half. Yeah. But see, between them, there's no real matter going in there. What you see is the threads going through there. So this is a cross-section of a star, essentially, what you're seeing there as well. That's what a star would look like. Okay. And this means that the field would go either upwards or downwards. It doesn't really matter. But the point is, it goes in one direction. And let's assume, because we all like to see north-south direction, here we have the north on top, we have the south on the bottom, and it's going from up to down. The threads are moving in this direction, right? And now what happens? They can't squeeze all these threads in there. So these stars have their threads moving very far away. Mm-hmm. And I would like to bet that maybe the fields of different stars also interfere with each other. And if they do, then where does that thread go? Well, I think that's the threads of the entire galaxy. They kind of push each other away.
Still, we're talking about the aggregate of donuts.
The aggregate of donuts.
Because Because you have a galaxy, it's made of suns, stars essentially,
Yeah.
and each star is a donut.
I hate to talk about donuts because a donut usually has a hole, and this guy doesn't have a hole. Remember,
It does.
It doesn't.
Well, okay, it's a
Because
very, very, very small hole.
No, it's not even a hole because remember you're squashing
Okay, but
atoms in there. There is no hole.
Okay,
That's
I
my
guess
point.
hole is the wrong word.
Yeah, there is no donut.
Okay, but
And the other thing is this is three-dimensional. In other words, it's not only a donut in the sense that like a torus. Remember,
but it's like
it's
wide.
a sphere. It's a sphere that has this toroidal. In other words, has the atoms aligned in a circular manner, but that doesn't make it a donut.
Okay, but it's like a widened donut. It's like a tall donut.
No, I hate the word donut for a sun because it's a good analogy to show what's happening with the alignment of the atoms and the molecules, if there are any molecules in there. In that sense, it's good. But where it's bad is that you get the idea that there's a hole in the middle, and there is no hole.
Okay. Then what would you call that shape?
A sphere. I call it a sphere.
We're gonna call it a blurb. I need a word for that.
I call it a sphere, and what goes through the center are the threads.
Okay, but what you're still saying is the galactic magnetic shape consists of an aggregate of spheres, of discrete spheres.
Yeah, that does. In other words, the spheres generate enormous threads, and these threads are circling the entire galaxy.
But then how do you have the same shape on the macro, the galactic shape, if it's just an aggregate of spheres? Wouldn't you just have a flat table?
Well, again, I think what happens is if you look at how many stars there are, I mean, they talk about billions and billions. If you talk to Carl Sagan, he'll tell you billions of billions. That's
billions and billions.
He's got billions and billions of stars in every galaxy, and that's probably correct, right? And and from our point of view, we say, oh, they're so far away. I mean, the closest star to us is
Sun, I hope?
I'm talking about to the solar system.
Okay.
Is Alpha Centauri. It's 4.3 light years away, and you say, well, that's a huge distance, And from a galactic point of view, that's petty 1 meter. It's nothing. But we're 2/3 of the way from the center of the galaxy. In other words, the galaxy is one. We're 2/3, 66% of the distance from the center to the edge. That means we're on the outer edge, and that's why distances are a little wider here. But as you get to the center of the galaxy, and I think you would see the distances are closer and closer together. In other words, the stars are closer and closer together.
But how does that explain the macro?
No, all I'm saying.
Shape. That's not a donut.
All I'm saying is that I think there's more chances of interference in the threads when stars are closer together than when they're farther apart. And I think most of that galactic threads maybe comes from closer and closer to the center. And again, it's got to do with the density issue. You get closer to a magnet, you get a higher field. I think you're going to get the same thing. I think if we go towards the center of the galaxy, for some reason, the magnetic field is going to be stronger.
Since there's more matter there?
Well, because the stars are closer together, I think.
Which means there's more matter. There's more matter cubic area.
Yeah, I think what happens is as you get out into the edges of a galaxy, it gets thinner and thinner and thinner as far as density. And this is one of the problems that dark matter has also, because they know that as you get out to the edges of the galaxy, there are fewer stars. The gravity is all in the center, and there's no gravity out there to keep the stars together. So what they did, they sprinkled dark matter in between, and that's how they obtained their results. But that's an ad hoc a solution. It's like a mathematical solution. If I pour kilograms in there, for sure I'm going to I'm going to be able to rotate this thing as a single platform. That's what they're doing. It's cheating,
Quick sci-fi question.
Oh, sci-fi.
Do you think
we go from science to sci-fi?
Yeah,
what is this? Quantum mechanics, relativity, sci-fi.
I'll bring some phi in here into the sci. Do you think the Goldilocks conditions on Earth you think one of the conditions of the Goldilocks is being so far away from the center of a galaxy where there aren't so much pressure or so many threads going through it?
Let's clarify. Goldilocks meaning it's not too hot, not too cold,
Right.
not too high, not too low, not
Yeah.
too one, not to the other. It's not in the extremes. It's just right. And I think
Essentially saying life couldn't be supported in on a planet that's just like Earth with the sun right next to it. But if you take the exact solar system and put it in the center or close to the center of a galaxy, would it still function the same?
yeah, I think that it's very likely that stars which are closer to the center of a galaxy where there's more gravitational field, more gravitational influence, more magnetic influence, I think maybe has different properties than our own sun. And they have made, again, it's a theory,
Yeah.
but it's like they believe strongly in it, and I kind of believe in that one as well. And that's that, there's a region where life can exist in a galaxy, and it's not anywhere. You can't exist. For example, if you were close to the center of the galaxy, we'd probably find no life whatsoever in any of those stars. And they say there's a region of what do you call it? It's got a special name, but something like the region of life, where life can exist inside a galaxy, and that's
I'm guessing it's in the middle of the.
no, it's like from the middle outwards, like where we are at.
Oh.
Obviously, we are in the right place. I
Was,
think
that
we
was
are.
actually a question on Quora that I saw once. If our solar system or Earth were in the center of the galaxy, would there ever be nighttime?
Well, you would get because of so many stars
so many
around.
s-
Yeah,
something
I don't
like
know about that. Maybe there some. It's like the going to the North Pole. You're up there and the Earth is spinning almost. You're spinning in the same place no matter where the Earth goes, and so you always get nighttime, that kind of thing. Yeah, in the same way, you probably go to the center of the galaxy, and it's just day every day. There's no night.
I think normal reality there looks so different that it's
You probably
it's imaginable, but I don't think we could put our finger on what it would actually look like.
Yeah,
There's so many
I think
variables.
you would need a lot of suntan if you're in the center of the galaxy because you get light from every star there. But as you come out there, I think you're gonna see some different types of stars and stars behaving in different ways. And again, I don't think you would find life probably in the first. If you look at the distance from the center of a galaxy to the outside of a galaxy, and you go halfway, I don't think you'll find life anywhere from the center to the halfway part of the galaxy. Life probably starts, in the region of life, which is beyond at least the 50% distance from the center of the galaxy.
So you're saying that no matter where the Earth appears in the universe, like let's say this Earth gets exploded or destroyed, wherever next we have life on a planet, and let's say humans evolve out of it, we'll never be able to see the center of a galaxy because we're always on the outside.
Right. All you can do, you can see the center of a galaxy when you look at another one. And again, what do we see? We see lots of things going on near the center of the galaxy. That's where all the action is. A lot of powerful things going on in there. And as you get out, it's more tranquil, calm. You go out there and, the stars are just twirling around.
Everyone's drinking mate.
Yeah, everybody's doing fine outside the galaxy. But close to the center, there's got to be a lot of action, gravitational and magnetic. And that's why I'm saying that, near the most of the magnetic field originates close to the center of the galaxy. As you get out, you get less matter, and you probably get less magnetic field. In fact, I would be willing to bet that a lot of those so-called black holes that they say are out there where stars are just twirling around nothing, I think they're closer to the center of the galaxy than they are farther out.
Why would they twirl around nothing not in the center of the galaxy? Like, let's say halfway through.
They do.
Down the
In
galaxy.
fact, they probably do. That's
why?
what. Because I think they've noticed that there's a lot of motion of stars near the center of the galaxy, and they attribute that to a black hole.
But I mean, away from the center of the galaxy.
Well, they're saying near the center of the galaxy. They say, they say every galaxy That's the current status. They say that they believe that every galaxy in the center has one because they have to have one because there's no other way they can imagine that.
Okay, but that's what I'm saying.
Okay, but any star, no, but hold it, let me finish. Any star near that point would be twirling around, would be affected not only by the gravitational field, but also by the magnetic field.
But do they say there are any black holes like on the edges?
Well, I haven't see these people never clarify where they found that star, whether it was in the center of the galaxy, in the middle of the galaxy, in the outer part of the galaxy. Now, I would be willing to bet that all those famous stars that twirl around nothing, maybe a lot of those are closer to the center or in the first half of that distance. I don't think that you'll find so many on the outside. Okay, anyways, just recapping a couple of the notions there. I'm saying that the threads are staggered as they sweep around a wire. So as the...
You mean magnetism?
The threads, yeah. In other words, the threads are staggered, and that's what causes the threads are twirling around the serpentine, and that's magnetism. Why don't they cross each other? Because they're staggered. The other issue is that, again, my dear son here, he comes up and he says the threads are probably both extended in opposite direction. I like that idea better than mine, so I've changed my religion last night. I thought it was a better idea also, partly because it's symmetric. I like that. Otherwise, you would have the situation where if the thread remains taut between two atoms and one is swinging, you have a lopsided, an unequal situation where it seems like you're pulling on one thread through all the ropes to create that loop while the other one remains straight. Whereas if you pull on both of the threads, like, here's my famous rope. If you pull on both threads like that, you open it up, then it's easier to understand. And so here's the rope, and it starts swinging. When it swings at a high velocity, the threads open up in both directions, in opposite directions. And I think that's really what's happening. And I think that's also what's happening inside stars that are close to the center of the galaxy. I think that there's a monstrous action going on in there. And so those threads are really trying to get, are swung around real violently. And there's so many of them that they have to extend far out because they just can't occupy the same region that the other thread's in. And then the other one is that, we have to look at that torus type of motion where the threads are coming through a hole that is tight on the inside and then expand on the outside. And that's essentially what's happening in a galactic, at the galactic field. They come in through the center, which is, you can say, narrow. You can have a few suns forming some kind of toroid there. And those threads, gazillions of them, just go through the center of that galaxy. Those are the famous jets that they always identify when they talk about black holes. And when those threads come out, they expand and they go on the outside of the galaxy, the gazillions of kilometers away. So that's what I think is happening. This, and again, it's a galaxy can be better viewed as a major toroid in that sense. There you can talk about toroid because the galaxy does have a hole in the center. It's not a black hole, it's an empty hole. They just go, the threads just go through there.
But it's an empty hole because there are so many threads going through. No star or planet could be there.
Maybe a star could be there and all the threads, maybe those are some of the stars that are twirling around near the center because the threads are coming through there and just twirling those stars around. And here I have a picture before we adjourn here. Where do I have it? And here it is. Look, this is one that I made, and you can see what's happening. Here's your star moving around nothing. What's coming down? What's coming down is the magnetic field. You have a magnetic flux coming down, and because the particle is charged, it's twirling around in a circle, and that's what we expect it to do because that is Fleming's left-hand rule. So wherever you check on the internet or any book that you have ever read, you will find that electricity moves in a coiling fashion. That's what we're seeing there. Why? Because it's in the under the influence of magnetic field, a magnetic flux that is pushing that ball to circle. And since it's going down in this case, right, going downwards, that's the motion of the particle, the ball, then it describes a spiral. And that's, I think, what's happening when we look at a star that is twirling around nothing. Not around a black hole, it's twirling around, it's twirling in a magnetic field. That's what it is. Okay, folks, anyways, I think we'll see you tomorrow. And we'll continue with a little bit of electricity. I never got to do resistors yet. 2 days in a row now. This tomorrow hopefully is the one where I get to talk about resistors. There's not much to say about them, but I think it should be covered because we have to explain how a resistor works under, the rope model.
Well, now that we talked about galaxies, I don't want to hear about resistors. That's too
too beauty compared.
Yeah.
Okay, folks, we'll see you tomorrow. Okay, bye-bye.